Hello and welcome to the 6th laboratory chapter for Operating Systems course. The topic of this video is shared memory segments and another inter-process communication mechanism to use when you need to establish communication between processes. Let's begin. Remember the last time when we utilized pipes to communicate processes? What we then did was defining a pipe, actually a special set of two files, between parent and child processes. In order to use the pipe, a programmer simply performs file read and write operations on it. Information written to a pipe from one process could be read by another process. Pipes offer unidirectional communication, which means you need a second pipe in order to also transmit data in reverse direction. In this video, you will be introduced to shared memory segments. But before we do, let's remember dynamic memory allocation mechanism in C language. When you use memory allocation function in C, a memory region with its size specified by the programmer is requested and allocated in the heap memory segment of the process. Until the memory region is destroyed with free function or the termination of the process, its contents can be accessed and modified by the owning process. A shared memory segment behaves similar to dynamically allocated memory. It is a location in memory that is created and accessed when requested, but instead of residing in memory regions of processes, it is independent from processes. Another difference is, shared memory segments are persistent. That means they keep staying in the memory even after all processes accessing it have ended. Dynamic memory regions will be released, whether you call free function in your code or not, but shared memory segments will stay in memory until a process releases them. Forgetting to destroy unnecessary shared memory segments will cause memory leak and quickly render large portions of your computer memory unusable until you shut down or reboot your computer. In order to communicate processes over shared memory segments, you must follow the following steps. Create or get identifier of a shared memory segment by using shared memory get function. Then, attach your processes to the segment using shared memory attach function. You may start using the shared memory segment exactly the same as a dynamic memory array at this point. When a process fills in this shared memory array, all attached processes will be able to access the values in it. When a shared memory segment is no longer needed in a program, it can be detached using shared memory detach function. When the shared memory segment is no longer needed by any processes, it must be destroyed using shared memory control function. Let's study the given codes. The first program requests the identifier of a shared memory segment with the key 1235. If no such shared memory segment exists prior to execution, it will first be created. Then the program attaches to the segment. If everything went normal, at this moment you should have a 50 characters long memory area reserved as a shared memory segment. The program simply fills this segment with user input, detaches from the segment and terminates. The second program again finds and attaches to the same shared memory segment, prints the message stored in it, and detaches from it. Now most probably this will be the last time the shared memory segment with the key 1235 will be used until the computer shuts down. So the shared memory segment should also be destroyed as it will not be used any further. When used with IPCRMID option, the shared memory control function performs this operation. Do you remember semaphores from the last video? It was explained that the second parameter of seminit function denotes whether the semaphore will be shared among threads of a process or separate processes. Setting this parameter to a non-zero value enables storing semaphores in shared memory segments and using these semaphores across multiple programs. The given codes present an example. The program below needs to read from a text file, but it can't yet proceed because sem wait will block this process. The required sem post will be called from the program above only after it has finished writing to the file. Both programs are able to communicate thanks to storing the mutex in the shared memory segment. Be careful when using shared memory get function with a numeric key. If you use a numeric key that is easy to guess, such as 1235 or 1236 in the previously presented codes, any user or any process may also attach and access the contents of your shared memory segments. This can especially be dangerous in public servers. In order to prevent such problems, shared memory get function provides usage of the special IPC private key. Such shared memory segments can be used with parent-child processes only. Finally, let's talk about some command line utilities. There are 3 utilities: IPCMK, IPCS and IPCRM that can be used to manipulate shared memory and other interprocess communication mechanisms as well from terminal window. As their names suggest, IPCMK creates a new IPC resource, IPCS shows a list of available IPC resources, and IPCRM removes IPC resources. You can learn detailed information about these commands by reading their respective manual pages. This concludes the 6th laboratory chapter. If you have any questions regarding usage of shared memory segments, you may use the forum in Web Online course page. Thank you for watching. Stay safe and stay healthy.